Okay, well, looks like it's just three of us. So let's start off with, do you guys have any questions?
Um, I guess I had some questions and then you answered them after I watched the full last meeting.
Okay.
So I said, are due dates correct? And you had made something further off because some people had gotten in touch. And I put sawdust with an exclamation point. So I'll tell you about that. And then that's it.
Okay. Yeah, there's the maximum expected for this class was 30, and then there were 47 people in it. So they ran out of books and lab kits. So I had to push meeting times back or due dates back for several spots. Okay. Okay, so did you guys have any questions about that first reading assignment? Anybody? No?
You answered the ones that I sent with my.
Okay. Most of you have taken the quiz, but not everybody, and some people forgot to submit. I'm not sure which people those are, but hopefully that gets done. And then the lab's going to be due soon. Probably only got 7 or 8 submissions, 7 out of 34 submissions. And the end of the chapter question thing seemed to be going well.
I have a random question, which I'm sure is wrong about labs. It says lab 1, lab 2 online, but there's going to be a bunch more, right?
Yeah, I just haven't made them available yet.
Gotcha.
Yeah, there's
I was like, God, this class is easy. 2 labs.
but do you see those ones you can't oh, I'm not sharing that with you just a second. All these ones are hidden. Are you seeing that now?
Oh, gotcha. Yeah.
Yeah. Okay. All right, so I feel like we kind of finished everything that we wanted to talk about with the first chapter. Yeah, because we finished talking about naming in 1.6, and I thought I think I might be getting my classes confused, but we talked about combustion, right?
Yes. No. Wait, did we?
I can't remember.
I don't think so. I know the chapter talked about it, but I don't think that you didn't either from the beginning.
Okay. Let's let me find a whiteboard. Pen. And let's see. I'll just use paint because it's easy. Pull that over there. Let's see. No, I need a pen. No, let's go red. Okay, so then we can do something like wow, that's really bad. Maybe it's just better if I type it. All right, so something like, let's do a really easy one to start off with. Okay, are we seeing this?
No.
No?
Mhm.
Huh. Why is that? How about now?
Yes.
Alrighty. Um, do you guys know what this molecule is called? CH4?
With chlorine? No.
No, it's one carbon and four hydrogens, and so the organic name for that molecule is methane, which you probably heard that word before. But that's the smallest molecule that's composed of carbons and hydrogens. And when you buy like a tank of propane or you have natural gas pumped into your house, that's one of the three gases that you're pumping in. So propane is just for some reason the name that they decided to use, but the difference between them is just the number of carbons. So then the next gas is this one is called ethane. Sounds a lot like methane, but this one's ethane, telling you that it's got two carbons in it. And then the one that you know for sure, that's propane. So there's not a lot of difference between them. All that's happening is I'm increasing the number of carbons, and because I do that, I have to increase the number of hydrogens. The molecule itself, let's do this. Insert a picture, and we'll go here, here, go. Alrighty. Grab a images. And that one's good. Open in a new tab. Copy. 1 second, I need to go kick a dog. Come here. Okay, so the methane molecule looks a lot like the ethane and the propane and the butane and the pentane. It's just that it's only one carbon. And can you tell now why we have to add hydrogens every time we add a carbon? Is that really obvious?
Because there have to be 3 hydrogens per carbon. Wait.
There have to be a total of 4 bonds to carbon, and you can see each one of those carbons is connected to 4 different things. The ones on the end need 3 hydrogens because they're only connected to 1 carbon, but any of the ones in the middle, since they're connected to 2 carbons in the chain, that means they can only be connected to 2 more H's. So every time you add a carbon, you add a couple of hydrogens, and the substance gets has more and more energy in it. So the smallest one is methane. And so if you have the methane and the ethane and the propane, that's natural gas. And all of those things will burn and they will all give you the same product. They will all give you carbon dioxide and water. What I think is the really cool thing about that, is 612. Oh, what's going on? Do we know what this molecule is? C6H12O6? It's very, very important to you or any animal. It's a sugar, it's glucose. So look at what's happening with that. If you take a sugar molecule and you expose it to oxygen and the reaction is allowed to happen rapidly, you get the exact same products that you would get for a methane molecule. So where do you find glucose? Where do you find, let's make that a little bit easier and call the glucose a sugar and then a sugar a carbohydrate. So where are you going to find a lot of carbohydrates?
Bread.
Pizza crust?
Yeah.
That'll work?
Yep.
Okay, so if you take a pizza crust and you eat the actual pizza crust, there are carbon atoms inside of that pizza crust. Where do those carbon atoms go? What do they get
Wait a
turned?
minute. You did talk. I remember this briefly. You said it comes out through gases in your breath.
Okay, so we did talk about this. So
Okay, so sorry. I just like now it's coming back to me, but like
that's okay.
Okay.
I've got 3 classes at the same time. So I never know which one I tell what.
well, I only have one, and I already saw this, and I was like, nope, we never talked about that. I just watched it today too, so.
Well, now you're getting it twice.
Which is good because
This is good, right.
So.
Okay, so just to refresh on this then, what you end up with is carbon dioxide and water. So you eat this pizza crust and it reacts with the oxygen and then you breathe the pizza crust out. That's pretty much what happens. It doesn't come out the other end, it comes out of your mouth because you're breathing it out as carbon dioxide. The same exact thing happens when somebody burns natural gas, so methane, ethane, or propane. You get carbon dioxide and water. It all ends up going to the same thing. So us using like a propane stove or using natural gas to heat your water or heat your house, it's producing the exact same things that you're producing as you walk around. So we're producing carbon dioxide. The problem with the environment is it's only expecting plants and animals to be producing and using carbon dioxide. It's not expecting trucks and airplanes and trains and whatnot using carbon dioxide. Do we know what the largest source of carbon dioxide is in the atmosphere? Man-made carbon dioxide?
Cars, vehicles.
It's not.
Really?
It would be nice to think that that's what it is, but that's not actually it. Can you, are you okay living without your car for a day or so?
Mm-hmm.
Maybe not Sky since he's in it, but you could probably live without your car. But could you live without, or could most of us live without any electricity? Like no electricity, no car, no phone, no lights, no heat, no hot water heater, none of that stuff. Is that something that people are going to be okay with?
No.
No, not now. So most of the carbon dioxide that's produced in the atmosphere is produced from burning coal, and that coal burning is used to produce electricity. So the point is with burning is we're doing the same thing that we're doing with a coal-fired plant or doing with your car or whatnot. It's just that the environment has never been situated to handle that much carbon dioxide being pumped into the atmosphere. It's only evolved to allow plants and animals to produce and use carbon dioxide. So we're not doing the environment any good service by producing more than we actually have. And yeah, I totally remember talking about that in this class now because we were talking about the Green New Deal and the New Deal and whatnot. Okay, let's, well, that was a review. Let's hop over and look at some stuff that is in chapter 2. All right. All right, so let's talk about have you guys started on chapter 2 yet? Do we know what the difference between these two gases is?
I haven't started yet.
I'm still waiting on a book.
Fun. Yeah.
Yeah.
Sorry about
He
that.
loves this right now.
So this is what you know as normal oxygen. So this is what you're breathing right now. This is what you would use to burn something or other. And this one over here, this O3, this is ozone. So the book talks in the first chapter about ozone being down in the troposphere, down around where we live, and it's a bad thing. And the reason it's a bad thing is it's highly destructive. So I want to talk about the destructiveness of the oxygen in this burning, and then we'll talk about the destructiveness of the ozone. So look what's happening to this methane molecule and this glucose molecule. So this glucose molecule, since we did talk about this last week, we talked about the fact that the trees and bushes and plants and wood and whatnot, the major component of that is glucose. So you take a piece of wood and you put it into the fireplace and it disappears in front of your eyes, right? It's not left at the bottom. It's not ash at the bottom. Because think about if you've I don't know, ran a fire all day or a wood stove all day, or you've been to Solstice and you see them pumping in the wood in that that big fireplace for the pizzas. They put that in all day long, and when they're finished, they're not taking out the same amount of stuff as they put in. Are we okay with that? Like there's definitely stuff at the bottom of your fireplace or your wood stove the next morning when your fire's out, but it's not even close to the amount of stuff you actually put in. So where did all that stuff go? It left it as this carbon dioxide. So most of the stuff turned into a gas and vaporized and went away. And all you're left with are really the salts that can't be burned, which are probably like potassium carbonate, which is called wood ash, which is something that people would make soap out of back in the day. And you can still do it today. It's just not as easy. But so what I want you to think about is, I mean, a piece of wood, say a piece of oak, that's a pretty sturdy object. What did the oxygen atom, or what did the O2, the oxygen gas, what did it do to that sturdy substance? It tore it apart. It was this structurally sound thing, and when the oxygen got finished with it, that piece of wood was turned into gases. It completely obliterated it, tore it apart, turned it into something not like what it started as, and it's gone. It is a completely different substance. So what we mean by this is that oxygen is really good at tearing things apart. And the O3 is about 100 times more effective. So do you want to expose yourself to O3?
No.
No, it will tear you apart. There's I can't remember if it was like on the Discovery Channel or whatnot, but it was a story about this kid who was someplace in the Pacific Northwest hunting with his dad and his uncle, and he was attacked by a bear. And his dad and his uncle weren't close to him when it happened, and it took him like 2 days to actually find him. And he had like a huge gash mark, like the top half of his right quadricep was gone, just completely gone. He had bite marks all over him, and he was gangrenous. So gangrene, that bacteria had gotten into his tissues and into his bloodstream. And when they took him to the ER, the doctor said, "We need to cut off your right leg." And he's like, "Listen, I hunt, I work on our farm, and I can't lose my leg. Is there anything else we can do?" So what they did is they shoved him into a hyperbolic chamber. And a hyperbolic chamber is something that it's basically just a gas chamber that you can fill it with any kind of gas you want. And so in this case, what they did is they filled the container up with 100% oxygen. So how much oxygen, what percentage of oxygen are you being exposed to right now? You guys remember? Ish. It's about 19 or 20%. So about a fifth of the atmosphere is oxygen. If 100% of our atmosphere was oxygen, we would all die in, I don't know, 6 to 12 hours. Remember when I'm
super flammable.
well, no, it causes flammability.
Mm.
That's a very big distinction. So you've got that word fire and the word combustion have sort of, well, I mean, they've got everybody in their head thinks about, oh, what that means. And what it means to a chemist is there's a molecule or an atom that goes in and takes electrons away from something and destroys whatever that something was. And oxygen is the second best substance at doing that. The first best substance is called fluorine. So it's the element right next to oxygen. But the best substance is oxygen, or the second best substance is oxygen. If you expose two things oxygen and fluorine, the fluorine would tear it apart even better than the oxygen would be able to. So that oxygen will go in and destroy whatever it comes in contact with. So what happens when oxygen comes in contact with super fresh, healthy tissue? It destroys it. What happens if it comes in contact with a single-celled organism? It kills it. So do you guys know why you put hydrogen peroxide into a puncture wound, but you wouldn't put it on like an abrasion, like a scrape or something? That fizzing that happens when hydrogen peroxide touches your blood, do you know what that gas is that's being produced? I'm sort of giving it away with this whole discussion.
I still can't guess what it is though. Oh. Oxygen?
It's pure oxygen. Pure oxygen comes out. So I have hydrogen peroxide and it turns into water and pure oxygen. And when that oxygen is inside that puncture wound, as it's trying to bubble out, if it just happens to run into, I don't know, a tetanus bacteria or a diphtheria bacteria or a cholera bacteria, it hits the cell membrane and tears it apart in the same way that it can tear apart a piece of wood, a wood molecule, a glucose. It's also tearing apart the cells that are you. But since you're made of billions of cells, it's okay if a bunch of them die. You'll survive. But when a tetanus bacteria has its cell membrane ripped apart from it, it's dead. So it's over. So what this
You're not supposed to use hydrogen peroxide a bunch on a healing cut.
on
Or
a
just-
you
It doesn't like actually heal.
right, it won't heal. You'll actually kill all the living tissue that's there. So if you have like you scrape your knee or you scrape your elbow or your hands or something like that, or you have a burn and you put hydrogen peroxide on it, you killed any bacteria that might be there, but you also killed all the cells that lived. So it's going to take a lot longer for that to heal. So the best thing to do with a surface abrasion or a surface burn that's not bad is to just wash it with soap and water.
Oh, sorry.
It's okay. Happens to me 10 times a day. So that kid that goes into that hyperbolic chamber, what they're trying to do is have the O2 kill the gangrene bacteria. And it worked. They put him in there and they had to take him out and they put him back in and they had to take him out. But the oxygen itself was able to tear apart the cell membranes of enough of the bacteria to have the antibiotic finish it off. So the end of the little video on this kid, he like pulled his pants down so you could see the top part of his quadricep and it just wasn't there. Like he could touch the bone. There was skin there, obviously, but he could just tap on the bone. But then when he pulled his pants down a little bit further, the bottom 2/3 of his quadricep looked like, I don't know, Arnold Schwarzenegger. It had taken over and gotten super, super strong so it could support the rest of him. But he was baling hay. So we're talking about this because we're talking about the ability of oxygen to tear stuff apart. And then I'm telling you that the ozone is about 100 times better at tearing stuff apart. So do we know where ozone comes from? How it can get produced? You know that smell after a lightning storm? That's ozone. Well, those are the byproducts of ozone. Ozone itself doesn't have any smell, but as soon as it gets into the atmosphere, it starts reacting with other stuff, and the stuff that it reacts with is what you smell. Or an electrical fire, you can smell that burnt plastic, but you also smell ozone. So the ozone stuff, you really don't want to be around it. We had a house fire in December, so I actually have an ozone machine that I'm running several times a week to try to make some of the stuff that we didn't want to have to get rid of not smell like a campfire with a bunch of plastic in it. But the ozone itself can tear molecules apart even better. So down here on the surface of the planet, it's bad because it can kill plants, it can kill animals. It's indiscriminate. It doesn't really matter. So that molecule seems really bad on the troposphere, but in the stratosphere, what do we know what its purpose is? Because that word ozone, you know it And in what?
Ozone layer.
In the ozone layer. So what is it that the ozone layer does for us?
Protects us from the sun.
Protects us from the sun and all the rest of the radiation that's in the in space. So there are we have the electromagnetic spectrum. So let me punch that in here. Insert a picture. And that'll be here and here. Huh. Weird spectrum. All right, I'm just gonna have to Google that again. All right. Electromagnetic spectrum. Images. So we'll do, oh, there we go. I like that one. Copy. Control-E. This a little smaller. Can you guys all see this graphic?
Mhm.
Okay, so what you're looking at here is radiation. And I know that sounds scary, but radiation is all around you. You're constantly being hit with it right now, and only some of it is a problem. It sounds like, I mean, radiation, so should I avoid all of it? And the answer is, one, you can't. It's impossible. And two, no. Some of it is, most of it actually can't do anything to you at all. Okay, so you understand X-rays, those things can be bad for you, right? I mean, they shoot through you, but it's not like doctors indiscriminately give X-rays because the X-rays themselves can damage you. Gamma rays, you may or may not have heard that term before, but those would be the most damaging. But I'm sure you've heard ultraviolet, and you wear sunscreen because you're trying to protect yourself from ultraviolet. And that's what ozone does for you. That's what this O3 molecule does in the upper atmosphere. It's protecting you from this ultraviolet. Most of the X-rays and gamma rays don't make it through the atmosphere for one reason or another, but the ultraviolet can make it through the atmosphere. Hence, you get tan when you're outside, or you get sunburn when you're outside. And the ozone layer is what's protecting, is what's keeping most of that ultraviolet light away from us. So what is it that's dangerous about the radiation? It's, so why are people freaked out by radiation?
Because it causes cancer.
Absolutely. The main reason is it causes cancer. So what I'm telling you is all of these radiations, the ultraviolet and the both types of X-rays and the gamma ray, those all can absolutely cause cancer. What is it about the radiation? What happens to you that makes you have cancer?
Your cells mutate or they start doing something weird.
Okay, same thing. They mutate because they're doing something weird. But what is it that gets mutated?
Your cells,
Well, what part of your cell?
the membrane,
Nope, not the membrane.
Isn't it the part that tells it not to keep reproducing or?
No. That's ultimately what ends up happening with the cell, that the new cell that gets generated ends up reproducing itself at an incredible rate. It's your DNA. So your DNA tells your body what to do, and if you mess around with the DNA, then your body doesn't know what to do with that cell. So, I mean, imagine you're trying to cook a complicated dinner and then somebody takes a bunch of pages out of the recipe and puts other pages in. Are you going to cook the right thing? No, and your cells don't make the right cells. So the issue is, to do that, you need to be able to break a chemical bond. And all of these different radiations, only these radiations have enough energy in them individually to break a chemical bond. So you might not know this or think about it like this, but visible light, that's radiation. Infrared, so just like the heat that comes off of a fire or your stove top or whatnot, that's radiation. Microwave, you probably do know that that's radiation. Radio waves, that's all radiation. So FM radio and AM radio, the radiation that comes in and out of your cell phone, all of those are radio waves. Do we understand what the scientific notation is for these numbers up top? Do we know what the difference between 10 to the third and 10 to the second is mathematically? It's just 10 times 10 times 10, or 10 times 10, or just 10, or 1, or 0.1. So this is how many times you multiply by itself, and 10, and this is same thing except I'm dividing. So this is equal to 1,000, and this is equal to 100, and that's equal to 10, and that's actually 1. So these are distances in meters. And these are the lengths of the waves themselves. So you can think about the radiation being a lot like a wave in the ocean going up and down. And so the distance between the tops of each of the waves, or the bottom, wherever you want to start and end, for the really long radio waves, they're literally 1,000 meters long, so a kilometer long, so 0.6 of a mile. And that wave is not nearly powerful enough to actually break a chemical bond. And the same thing with these other types of radio waves, and the microwave, and the infrared, and the visible light. None of these waves are strong enough to actually break a chemical bond. It's not until you hit after purple. So do you guys remember that whole Roy G. Biv thing from like art class or something like that? Red, orange, yellow, green, blue, violet give you the colors of the rainbow. So red on this side, which is why this is called infrared, and purple or violet on the other side of the rainbow, that's why that's called ultraviolet. It's not violet, it's past violet. And once I've passed the violet color, that radiation now has the ability to damage cells. And what we want as humans is that ozone layer in the atmosphere, this ozone, to block that radiation from coming down and causing cancer. It's really, the odd thing about it is people who are not dark-skinned, they are susceptible to this. But somebody who's actually like from Africa, they don't have skin cancer. The only place they can get it is in their mouth, on the palms of their hands, the palms of their feet, and underneath their nails. That's it. There is no, they just simply don't get it. What the reasoning is, they already have the melanin in their skin to protect themselves. So that dark color is what protects you from UV damage. And you only get that once you're very, very tan. But to get very, very tan, you must have exposed lots of yourselves to the bad radiation. So it's not like something you should try to do. You're definitely much more susceptible on your way to getting a tan than making it worthwhile to you. So this O3 is the protective shield around us, making sure that we don't get cancer from ultraviolet rays. But if it's down in the troposphere, it becomes really bad for us because it's really good at tearing stuff apart, like the cells inside of your lungs. All right, so next thing I want to talk about would be, let's go up here. I feel like we talked a little bit about periodicity last time.
Instances where you'd get exposed to too much oxygen, like to ozone, is that just, I mean, I know
To oxygen or to ozone?
to ozone. Like in the last chapter it touched on it, but I'm just curious, like relating to everyday life, like, you know.
Fires,
Fire.
electrical fires, coal fire plants, the picture that's on, let's do, since Sky doesn't have a, let's do it like this.
Alright, I'm adding the picture.
Atmospheric. Copy. All right, we seeing this one here, the atmospheric inversion.
Mm-hmm.
It's inversion layer. So what ends up happening with this is you'll have this weird situation where there'll be a block
a big like mattress of air of a different density, and then another type of air on top of that with a separate density, and then this air that's supposed to be trying to get out can't, and it gets stuck in there. So you end up recirculating this. So you end up, the ozone that does get produced by industrial processes that you would expect to just float away in the atmosphere ends up staying here. And this is something that happens a lot in the Dalles because of the geography of the mountain range, the way the river turns, and it just ends up spiraling and eddying over the top of the Dalles. And we talked a little bit about this last class because you know that there's a temperature inversion. So what you would see with this particular situation with this graphic is it would be nice and clear up top here, and it would be very smoky down here, and you would see smoke going up out of a stack, and then all of a sudden it would take like a 90-degree turn, and it wouldn't be able to break through the inversion layer. So you would know if you're in the Dalles and you're looking out and you're wondering is it an inversion day or not, just look to see somebody who's burning a wood stove or a fireplace. And if the smoke just continues to go straight up, then you're okay. But if it turns dramatically at some point, then that air is stuck in there. And you're just rebreathing air that's basically pollutant. All right, so let's see. So last time we were talking about the periodic table, and we were talking about groups, how those things chemically react similar, and the columns and the rows, they do not react similarly. At one side you've got one type of substance, and the other side of the row you've got a completely different type of substance. We didn't talk about what these numbers mean, the 1 and the 1.094. So this number 1 is telling you which element we're talking about, and their number is based off of the number of protons inside of that substance's nucleus. So hydrogen atoms have 1 proton. If you're an atom and you have 1 proton, you're a hydrogen atom, no matter what. If you have 2 protons, then you're a helium. If you've got 3 protons, you're a lithium. If you've got 6 protons, you're a carbon. And 11 protons means you're a sodium. But let's talk about the number underneath. So why is this number right here not equal to 1?
Did you change the picture on the screen?
I did. You're not seeing a
I was
periodic?
seeing the inversion layer.
Really?
Yeah.
Damn. Why does that keep happening? How about now?
Got it.
Okay. Okay, so the question is, why is this not a whole number? So what we have to talk about for a sec is what the atom is composed of. So let's do... Okay, so any given atom is going to be composed of protons and electrons and most likely neutrons. So the protons themselves, you're going to find those things in the nucleus, which is the thing at the center of the atom. And you're also going to find neutrons in the nucleus. The electrons, you're going to find these things in orbit. So these guys are going to be found in orbit around the nucleus. The proton has a mass of 1. The neutron has a mass of 1. And the electron has a mass of 0. So that mass number equates to these numbers down here at the bottom. So what we have is an interesting circumstance where every single hydrogen atom has to have what in its nucleus? What did this 1 mean?
1 proton, 1 neutron.
Nope, just 1 proton.
One proton, okay.
So that 1 right there means 1 proton. This 3 right here means 3 protons. That 4 means 4 protons. So this down here is the mass. It's actually the average atomic mass of hydrogen atoms. So why is that number not just 1 if a hydrogen atom has just 1 proton in it? It's because there's different types of hydrogen. They all have 1 proton in them, but some of them have 1 proton and 1 neutron. And some of them have 1 proton and 2 neutrons. But most of them have 1 proton and 0 neutrons. How do you know that? I said this was an average weighted mass. What does that weighted word mean when I'm taking the average of something? If you were taking 4 classes and you got 3 A's and a C, is your GPA a 3.0? Or is it higher than a 3.0 because you got 4 A's and you only got 1 C? Isn't your GPA above a 3.0?
Yeah.
It is. So that's what a weighted average means. So this number is 1.00794, and what that's telling you is most of the hydrogen in the universe has a mass of 1. And very, very few of them have a mass of 2 or 3. Does that make sense? Let's skip over here for a second. Look at the helium. So what does that 2 number mean?
2 protons.
That all helium atoms have 2 protons. Can you tell me what most heliums also have in them? Based off of the mass number? Sorry. There we go. Does it make sense that most heliums have 2 neutrons in them? Protons have a mass of 1, neutrons have a mass of 1, electrons have a mass of 0. Every single helium has to have 2 protons in it. Required. If it doesn't have 2 protons in it, then it's not helium. But most heliums in the universe have a total mass of 4. So where's the other 2 coming from for the mass? Neutrons. So what about this carbon? What do you know is in the nucleus?
6 protons.
Has to have 6 protons because it's a carbon atom. And most carbon atoms in the universe have how many neutrons in the nucleus? Yep, because that mass is almost 12, right? And I know 6 of that mass has to be protons, so the rest is neutrons. So then most carbon atoms have a mass of 6, or a mass of 12, meaning it has 6 neutrons in it. But you can see that the average weighted mass is 12.011. So that means there must be other carbon atoms out there that are heavier and have more neutrons. And there are. There's a carbon 13. So what that means, the way that gets written, let me come down here. What this is telling you when it says C13, let me back up. Let's go C12. So what that is a carbon atom, and then this particular carbon atom has a mass of 12. Well, since I know all carbon atoms have 6 protons in their nucleus, then this carbon atom must have also 6 neutrons. So tell me about this carbon.
It's going to have 7 neutrons.
So that has to have 6 protons again because it's a carbon atom, but now it's got a mass that's would need 7 neutrons to equal up to 13. And so then what about this guy? We okay with that being 8 neutrons? The total proton number and the total neutron number have to equal that total mass. Have you heard of that, the term before, carbon-14? How about if I said carbon-14 dating?
Yeah.
Oh, yeah.
it tells you how old like a spoon, a wooden spoon is that they find in an archaeological dig in, say, I don't know, Uganda, wherever. So what that's telling you is that the carbon itself is that when it has a mass of 14, it's radioactive, and the other ones are not. That's a side point, but the important thing to know is the reason that the mass on the periodic table for carbon is 12.011 is because it's a weighted average of all the different types of carbon out there. And these different types of atoms with different numbers of neutrons in them, they're called isotopes. So what you're looking at are the three main isotopes of carbon: carbon 12, carbon 13, and carbon 14. So are you okay with me saying that most of the carbon in the universe has a mass of 12? Why is that? Why is that a reasonable statement? Because on the periodic table, the average weighted mass is 12.011. So what that's saying is most of them have a mass of 12, but there are a few that have a mass more than 12, which makes the average a little bit larger than 12. Tell me what most neutrons have in their nucleus. Are you okay with me saying they all have 7 neutrons or protons?
Mm-hmm.
So then if their mass is 14, then they all have what in the nucleus as well?
2.
7. So if it has to add up to 14, and I know 7 of it is protons, then the other 7 of it has to be neutrons. So 7 protons and 7 neutrons gets me up to a mass of 14. For this oxygen, since they all have 8 protons in them, and then this is really, really close to 16, right? So that means most oxygen have 8 neutrons in them to go along with the 8 protons that they have to have. Tell me about sulfur. It's got 16 protons in it, right?
And 16 neutrons.
And since 32, I can just cut it in half, and I know 16 of those are protons and the rest are neutrons. But what about this? Let's go with, let's do an easier one. How about this mercury right here? Hg.
Gonna have 120 neutrons.
Yeah, all mercuries have to have 80 protons. That's what makes a mercury. But most mercuries have a mass of around 200, so the entire rest of the mass has to be due to the neutrons. So then that most of those mercuries have 120 neutrons in them. As the atom gets bigger, you end up having more and more neutrons relative to your number of protons. So all you're doing is subtracting. So if I subtract 80 off the 200, I'm left with 120. So most mercuries have a mass or a number of neutrons equal to 120. And again, these things are called isotopes. So let me stop sharing that for a second. Pull this, go there, and go there, and come down here. Okay, let's go back and share this guy. Okay, so this table is just like a question kind of thing you could be asked about isotopes and about what it is that you're looking at. So before we try to fill this thing out, the first thing that we need to think about is for every single atom you have, whatever your number of protons you have to have, the number of electrons has to be exactly the same. So your proton and your electron number are always going to be exactly the same value. All right, so how do we have 2 empty spots in this first row here. So how are we going to fill that in? So you find Na on the periodic table. Have we find that? Do you guys have a table?
I have a table, it's just hard to find it right away because it's small.
Yes. Na.
Yeah. Which number is it?
It's 11.
There you go. So that means that its atomic number is 11. And what is that atomic number telling you it has?
11 protons.
11 protons. And then what did I just say about protons and electrons in an atom?
So if you,
No, protons and electrons.
I want electrons, okay, never mind.
They're exactly the same value.
Okay.
So I've got these 11 protons, which means I have to have 11 electrons. And this particular sodium, I'm telling you, this isotope of sodium has 12 neutrons in it. So if I take my proton number and my neutron number and I add them up, then the mass of this particular sodium atom is a mass of 23. So this would be sodium 23 because its total mass has a mass of 23. So now let's go down to the next row and try to fill this in. So this, whatever element this is that we're talking about, whatever isotope we're talking about, it has an atomic number of 15. So what element has an atomic number of 15?
Phosphorus.
Phosphorus. So I'm going to put a P right there. And any atom with 15 protons has how many electrons?
15.
15. This phosphorus has its 15 protons and it has 20 neutrons. So what's its total mass?
30.
35? Agree with that? It's the proton number plus my neutron number. Remember, my electrons don't have a mass. Their mass equaled 0. Okay, so let's go down to the next row and fill this one in. Using these two pieces of information, how are we going to fill in these other empty cells?
Find the atomic number that has 92.
Okay, so since the proton and electron number have to be the same thing, I'll put 92 in for the atomic number. And who's got 92 for its protons?
Mm,
You. I'm
You.
not sure what that
Uranium.
is.
All right, so we got uranium in for the symbol, 92 for its proton number. This particular uranium has how many neutrons in it? How do you get that number? We're okay with,
146.
yep, 146. And you get that from taking your total mass and subtracting off the fact you know it has 92 protons in it. And so what you're left with is the number of neutrons. How about this Ti, this titanium? What number is titanium?
81?
No,
Oh,
no,
I
no.
was wrong on that.
That's
Uh,
thulium.
I saw TL. You know what? This is not in Courier. Looks like an L.
22. So if it's got 22 protons in it, it's got how many electrons?
22.
22. This titanium also has 25 neutrons in it. So what is the mass of this titanium?
47.
47. Excellent. All right, so this last row, I've got something with a mass of 22. It's got 11 electrons. So how many protons does it have? 11. So what element is it?
And A.
It's sodium. And how many neutrons does this sodium have? You okay with 11?
Yes.
Because the 11, the atomic number and the number of neutrons, so protons and neutrons, equals this 22. So you can absolutely have a sodium with a mass of 23. You could also have a sodium with a mass of 22. Which one's more common? How are you going to figure that out?
having the chart with the average.
Yep, having the chart with the average. So here we go. There's a sodium. It's got its 11 protons. There's the Na. And this guy's mass is really close to what?
23.
Yeah. So most sodiums have how many neutrons to go along with their 11 protons? 12?
Well,
Excellent. Okay. Does anybody know why in an atom the proton and electron number are equal to each other?
for balance,
Yeah, but what is it that they're trying to balance out?
there's wavelength.
No. So protons, neutrons, and electrons. The protons have a positive charge on them, and the electrons have a negative charge on them. So if I've got an atom with equal number of protons and electrons, what's the charge on the atom?
0.
0. And all atoms have a charge of 0. That's what you're going for. So if you're holding like a charcoal briquette, that's basically pure carbon. Every single one of the carbon atoms in that charcoal briquette have 6 protons because they're carbon, and since it's an atom, they also have 6 electrons, which is why you can grab it and it doesn't shock you or something. It's got a set number of protons and electrons, and they're equal to each other. Okay. Talk about your structure.
What does cause something to shock you? I'm just curious because ever since I bought my car, every time I get out and I go to close the door, I get a little shock on my fingers.
You have, is it a new car?
No, it's like a 2002. So it's like this old Tahoe like carpet, but I got rubber floor mats and it still shocks me. I don't know. I thought I was just dragging my feet on it or something. But
There's probably an electrical wire somewhere that's touching something it's not supposed to, like maybe a piece of insulation that's worn off, but not very much of it. And so you end up accumulating a charge probably on some maybe like a seatbelt or anything that would be able to hold a charge, which would be something like your carpet or the seatbelt or the, I don't know, any fibrous something or other has a possibility. But usually in an old car, that's because some wire is barely touching some piece of metal that it's not supposed to touch.
even like a static shock though, is that kind of the same thing? I know
Yeah, the static shock gets built up over a period of time, and it's just sitting there waiting to be discharged. And it definitely wants to be discharged.
should have taken this class a few years ago.
Nature-
I ride my car all the time.
Nature does not like static charges, so it wants to put that proton and electron back together where they belong, and that's what's happening with lightning. You get a buildup of electrons, usually on the ground. It doesn't really matter which direction, but they skyrocket upward or downwards to put the electrons back where they're supposed to be. Alrighty. Do we know why there was a hole in the ozone layer?
No.
Nobody? Let's stop sharing this guy. Let's go back to this other one. Is it this one? Nope.
Because of burning coal.
No, but it's a good answer. It's almost always that's usually the cause, but in this case, it's not the case. So remember what we were saying about this oxygen, the ozone?
Mhm.
It's really super reactive, right? So what it wants to do is take electrons from anything at all, and what happens in the upper atmosphere is just 1 second. See if we can find a decent picture of that. Hmm. Is that one okay? That one's fine actually. Let's copy, drop this camera. Actually, no, that one's terrible. Okay, so the ozone molecule is 3 oxygens, and when this ultraviolet light that can cause cancer by breaking a bond in your DNA, that thing breaks it apart. So what you end up happening is you'll end up having regular O2 in the upper atmosphere, and then just this one oxygen off by itself. And oxygen hates to be by itself. So usually what happens is it collides back with itself and turns right back into ozone. So the awesome thing about ozone layer is it blocks the radiation by breaking itself into 2 pieces, and it hates to be like that, so then it just puts itself back together. So you have O3 breaks into O2 and O, and then goes right back to O3, and it blocks another radiation from the sun. And so it just keeps self-healing. The bad thing happens is when you end up, I don't know, all right, that's not exactly what I wanted. The bad thing that happens is when a particular type of molecule that has chlorines and fluorines in it gets involved in the situation, the chlorines and fluorines, when this oxygen is broken apart, the molecule with chlorines and fluorines in it grabs it. And then that oxygen is not free to go back to the O2. So what we've been doing is creating these molecules that make their way up into the upper atmosphere, that when the ozone breaks apart because it blocked radiation, it's not allowed to come back together. And those molecules are mostly used in refrigeration. And most of the world banned their use sometime in the 80s. And the ozone hole actually got smaller for a decent time period. And this is what it looks like right now. So there's Antarctica. And so you've got this huge area where there is really no ozone protecting from the sunlight. It's not the worst thing in the world, though, right? Because who's running around Antarctica like in a bikini? That's
Maybe like
not.
3 scientists.
Yeah.
A couple of ones or something.
Yeah, I'm sure it's happened just so somebody can take a picture of it, but it's not like it happens all the time. So most people are completely covered up because it's obviously really freaking cold down there, so you're not super worried about it. Why is it down here anyway, since most of the atmospheric pollution is caused by people who don't live in Antarctica? Why is it there? The atmosphere is a fluid. Fluid moves. The thing underneath the fluid is spinning. So the planet is spinning. So if you take let's say you take a basketball and you put it into a little kid's swimming pool, and right before you put the basketball in, you spin it, and then you set it into the pool. What's going to happen to the water around the basketball? It's going to start whirlpooling. We okay with that? It's going to cause the water to actually move. Does that make sense? What happens when you flush your toilet? Maybe this is a better way to go. Does the water just go straight down the drain, just fall? No, it spins, right? It's called the Coriolis effect. So the toilet is literally spinning underneath where the water is. So the water is turned into a vortex to go down. So what ends up happening is the atmospheric pollutants, these molecules that have chlorines and fluorines on them that are destroying the ozone layer, get funneled down to the top and the bottom, because that's what happens to waste. Just like your toilet spins and flushes stuff down, the same thing happens with the ozone layer. You end up having all the pollutants in the at the points where the spinning is occurring, which is the North Pole and the South Pole. We would be a lot more alarmed about this situation if that hole was, say, right over Kansas. That'd be a much bigger problem. And I said a minute ago that the ozone layer is getting smaller, was getting smaller, and it's not getting smaller anymore. Does anybody have any idea why?
Pollution?
Some country that told everybody that they wouldn't make chlorofluorocarbons decided to start making them again. What country would be big enough to have a global impact? China. We've detected a bunch of molecules that are banned substances in atmospheric currents that come out of China. And so the reason the ozone layer is increasing in size again is because China's using a bunch of illegal chemicals we're not super sure what they're doing, because you don't need them for refrigeration anymore. We've come up with different molecules that do the same thing. But for some reason, the ozone layer is getting bigger and it's China's fault. We obviously need to stop that, because if there was no ozone layer, you would have to go out completely clothed from head to toe, and you'd have to wear like zinc oxide all over your face, or wear a mask, because you wouldn't be able to withstand unozone blocked UV. You would burn almost within like 3 minutes. You would have a severe sunburn, and you obviously wouldn't be able to do anything. Plus, your level of getting cancer would be pretty huge. Oh, there's the picture I was looking for. So when chlorine comes in contact with the ozone molecule, it takes one of the oxygens away, and now I've got this thing. This is terrible at blocking UV. It doesn't block it at all. And the oxygen, O2, can't block it. And so what you end up with is the protective coating just being disassembled, because remember what it is that ozone likes to do. It likes to attack stuff. So it attacks this chlorine, and now I've got this molecule, and this molecule doesn't do anything for me, and neither does the O2. All right, let's see what else we got here in the book we want to talk about. Let's talk about, nope, not there. Let's go down here. We should probably talk about nomenclature again, since you guys weren't here. Yeah, why don't we do that? Zoom go here. Let me go here, share that. Okay, actually, I want to start up here. So in the last class, we were talking about the different substances on the periodic table. You guys are seeing this metal and non-metal thing, right?
Mm-hmm.
Okay, so most of the elements on the periodic table are actually metals, and some of them are non-metals. You have, on your periodic table, there's going to be some sort of darker line stair-stepping down here, and that's separating your metals and your non-metals. These ones that are blue that are touching it, they're called metalloids, so they kind of do some of each of those things. There are at least 5 different ways to name molecules. There's ionic, there's covalent, there's acids, there's organic, there's biochemistry. So there's lots of different ways we can name it. And so with this first chapter, we are concentrating on being able to name things in the simplest way. And the simplest of those nomenclatures is called the covalent nomenclature. And a covalent bond happens when things over here that are green, all of these green guys, react with other things that are green. So nonmetals making a molecule with other nonmetals, that's a covalent compound. So the covalent compounds, how they do that is they end up sharing electrons. Instead of doing an electron transfer, they share it. So what you need to do when you're determining how to name a substance, the very first thing you have to do before you name it is, what kind of molecule is that? You need to start off with that. So in this case here, I'm looking at these two atoms, and here's carbon and here's oxygen. And if I go back up to my periodic table, the carbons and oxygens are both nonmetals. So that means I named this covalently. Conversely, if I look at like this substance here, this is CaCl2. So all right, I've got a calcium and I've got a chlorine. So if I go back up to my little periodic table, here's my chlorine over here, so that's a nonmetal. And here's my calcium. Well, that's a metal. So that's a metal and a nonmetal, and that's not a covalent compound. So I don't get to use covalent nomenclature to name that thing. So when I come back down here, I find this carbon and this oxygen. I want to name these guys covalently. So I said that this was the easiest nomenclature system, and it is. The thing that you need to know is this list of prefixes. We know most of those, right? Monodi, tri, maybe tetra, but you might know that from geometry. And then pentagon because of the Pentagon building, and hex is 6. Hept is probably not something you know because 7 isn't used all that often. And then oct from like, I don't know, MMA, the octagon fights. And then non, also probably not something you recognize, but that means 9. And then dec, you know from decade, so that's 10. So 1, you need to know what those prefixes are, and 2, you need to know 2 other rules. The first rule is if the first atom in the molecule is by itself, you don't say mono, but you use a prefix at all other times. That'll be clear to us when we go down and do a couple examples. And then the second part is whatever the second atom is, I hack the end of it off and add the suffix IDE. So table salt is sodiums and chlorines, but when we say table salt, we say sodium chloride. So we're just going to tack an iodine to the end of each of these things. Okay, so this guy is carbon monoxide. So how come that name makes sense? 1, I know it's a molecule composed of 2 nonmetals. Carbon is a nonmetal and oxygen is a nonmetal, so I end up with carbon monoxide. The first one is by itself. And when the first one is by itself, I do not say mono. So this is not called monocarbon monoxide. But the second one, if it is by itself, then I do actually use the monoxide prefix. So I've got carbon monoxide. So what happens if I were to change this subscript to a 2? So what would this one be called?
Dioxide.
Carbon dioxide. Great. Okay, so
I
you're...
want to know about just the single oxygen though. So if it's monoxide, so oxygen, like how do you decide how much of the word to cut off before you put the I in? It's just kind of common because like we know that is normally, but like what if it's something that I'm not?
You're always going to be doing this with the nonmetals. The nonmetals are always written second. So then you're always going to be saying the "ide" portion with the nonmetals. So let's find a periodic table and let's talk about that for a sec. I actually have never heard that question before, but it's a good one. So, okay, so there's a carbon. How would you add the suffix to the carbon if the carbon was second?
Dicarbon?
No, forget about the prefix portion of it. Let's say there was just a carbon there and you wanted to, so like with oxygen, we call that oxide, right? And chlorine,
Okay.
we call that chloride. What would you do with the carbon?
Well, I have this bookmarked in my book with carbon. If it was 2,
No, just how would you add the IDE suffix to that?
carbide.
Nailed it.
Carbide? I don't know.
Carbide, you were right the first time. So this one's carbide. What would nitrogen turn into?
Nitride.
Perfect. We already know oxide. What would fluorine be?
Right.
You know fluoride, right? I mean, it's in your toothpaste. And chlorine turns into
Fluoride.
chloride. Sulfur turns into
Sulfide.
Sulfide.
All right, I'm getting this.
phosphorus,
Phosphide.
phosphide, bromine.
I'm convinced somebody else is spelling this is very hard.
Well,
Bromide?
do it like this. Fluorine, chlorine, bromide,
Mean. I got
right? Chloride goes to bromide. The last one here is iodide. You don't have to worry about AT because there's literally about a teaspoon of it on the entire planet because it's radioactive. You don't have to worry about any of these guys, the last column, because these are all noble gases and they don't chemically react with anything. So they're never going to be high, I don't even know how to say it, argide. That's not going to be a thing because argon doesn't chemically react. Selenium, do you know that word?
Yes, I just don't know what it means.
It's just an element that you need a very tiny bit of it in your body to make sure that one particular enzyme functions correctly. So you're almost never going to see it, but it's selenide. So that's the one that I think sounds the weirdest. But the rest of these you kind of get. It's sulfide, it's chloride, it's bromide, it's iodide. So that's how you tack the IDE onto the end of those guys. But if we, let me kill this. Let me pull up something else. Worksheets, nomenclature, covalence. So let's save that, share that. Are you guys seeing this ammonium sulfide thing?
Yeah.
Okay, so let me find some. Okay, so again, we're only naming the covalent ones. So can you name this one right here? What's the first thing that you're supposed to do?
Well, we know that the first thing is single.
No, before you do that,
Yeah.
you look at that and say, okay, there's a calcium there. Okay, wait a second. Calcium's a metal. So I can't name this as a covalent compound. So we haven't learned how to name this thing yet. So you'd skip over that one for now because we didn't talk about that. And that same thing, aluminum, you know, is a metal, right? So we're not naming that one. Potassium is a metal. Sodium is a metal. So we can't even name these first 5, 6, 7, 8, 9, 10 of these guys. All of those have metals in them, and we haven't talked about naming that, so we're going to skip those. But what about the other side over here? Can we name this one? Can we name 38 and down? Find phosphorus and chlorine on the table. Where are they?
We're in 17.
But what side of that stair step are they? The left side or the right side?
It's the right side.
Both of them are. So then that means that that's a non-metal reacting with a non-metal. So that means that's a covalent compound. So then you're going to use covalent nomenclature to name it. And so the phosphorus is by itself, and then there's 3 chlorines. So, but the phosphorus is first. So how do you name 38?
Phosphorus tri.
That's it. Phosphorus trichloride.
I feel like I'm talking too much, sorry.
So what about 40? 38 is phosphorus trichloride. What's 40?
Phosphorus pentachloride.
Perfect. Phosphorus pentachloride. What about 41?
diphosphorus pentaoxide.
That's it. Diphosphorus pentaoxide. 42.
Sulfur dioxide, no.
No.
Disulfur, no.
Yeah. Disulfur. You're right.
Disulfur dichloride?
Perfect. Disulfur dichloride.
Okay.
Can you come up with the formula for number 70 here?
So it'd be
N2O3.
Perfect. N2O3. How about number 69?
SO3.
SO3. Yep. Got it. How about 71?
N2,
Oh,
oh, yeah.
Yep. N2, just O, right? Yeah, that's laughing gas. That's nitrous oxide.
I laughed.
How about 61?
Can't see it. Oh, there you go.
AS4. What is? Let's look it up.
Oh, what?
10.
10. Yep. AS4, because tetra is 4 and dec is 10, and so there's 10 oxygens there. So AS4, O10. So you guys feel okay going back and forth like that? Starting with the molecule and coming up with the name, and starting with the name and coming up with the molecule?
Yeah.
Okay. Alrighty. Let's go. All right, I want to talk a little bit about something called the Lewis structure. Let me pull a few of those up. Copy image. Paste image. Why is that not working? All right. I'll just do this. Alrighty. Go back here. Go over here. Go right there. Okay. Do we see the Lewis dot structure there?
Yes.
Okay, so all the Lewis dot structure does for you is it makes it easy and tells you how many electrons that are around a particular atom that are going to chemically react or that are available to react. So if you look at nitrogen on the periodic table, can you tell me how many electrons a nitrogen atom has total? How do you figure that out?
Nitrogen. I think it has 7.
It has 7 protons, so that means it has to have 7 electrons. Perfect. So how come only 5 of them are drawn here? These are the only ones that'll chemically react. The other two are completely and utterly off limits. They will not react under any circumstance. So how do I know that it was 5? What you do is you grab yourself a periodic table. Like this one's fine. And then you just run across the table. And so anybody in this column right here, the first column, has 1 dot, which means it doesn't matter how many electrons they have, only one of those electrons are going to chemically react. So if I was going to draw the Lewis structure for, say, a lithium, it would just be an Li with 1 dot. Or for sodium, it's an Na with 1 dot.
And is that just because it's in the first line?
Yep, it's in that first column, and that's what it means to be in the first column. It means you only have 1 electron that reacts. And that's why those guys are all in that same column, because they all only have 1 electron that reacts. So
And does it go across, like the second column has 2 electrons?
Yep. Column number 2, the beryllium column, every single one of those elements, the magnesium, the calcium, strontium, all of those guys have 2 electrons that will react. Even though calcium has 20 total electrons, 18 of them will never do anything. Only the 2 on the outside will react. So do you see on this chart here, it says 1A, 2A, and then it goes to 3B?
Yeah.
Skip over all of those B's. We're not going to talk about those right now.
Okay, so just go over to the A. See, because mine doesn't have that. It's kind of different. I'm gonna probably upgrade my chart or just something that has.
I bet it does. Look at the very, very top of your columns.
Yeah, I mean it does, but it goes from 1 all the way to 18.
Uh,
Like it doesn't.
Actually, that's funny because that's the way that most people are doing it now. So this thing that says A's and B's, that's old.
Okay.
So your table is newer. So how about this? We're only going to talk about that raised portion of the periodic table for now. And that lowered portion that starts off with scandium, we're going to skip that for now.
Yeah.
Okay, so column number 1, all of those guys have 1 electron. Column number 2, they all have 2 electrons that can do anything. We're going to skip over that entire middle section and then go to boron. Every single atom in the boron column has 3 electrons that will react. Even though boron has 5 total electrons, only 3 of them are going to do anything. So what do you think's happening with the carbon column?
Gonna have 4.
4 electrons. Everybody in the carbon column has 4 electrons to react. How about the nitrogen column?
5.
They all have 5 electrons to react. And the oxygen column?
6.
6. The fluorine column?
7.
7. And then the last column, they don't react, so it doesn't really matter, but you could throw down 8 for neon and everybody else that's below neon. So let's go back over to...
What is the lanthanide or an actinide series? I've had this weird thing where it's like the bottom of it has these 2 different. You
Yep.
see what I'm saying?
Those guys are disconnected. Let's talk about that in a sec.
Okay.
So this is why this is why nitrogen has 5 dots around it for its Lewis structure. What it's trying to say is, I've got 5 electrons that can chemically react. Even though I have 7 electrons, 2 of them don't react. So how did I know that to put 5 electrons around that? I grabbed the periodic table and just counted over till I got to nitrogen, and that was the 5th column, excluding that lower portion. So if I was going to throw up, if this was going to get turned into oxygen, what would I do? I put an O right here, and then I would add 1 more electron. Because oxygen is 1 column over, so that means oxygen would have 6 total electrons. So let me grab that.
Sure. So there's oxygen's Lewis structure. What does it look like for, say, chlorine?
Seven.
Yep, it's got 7 dots around it. So here's chlorine's Lewis structure. So all that's happening here with these Lewis structures is you're being told how many electrons will actually do something. So how many electrons does a chlorine atom actually have?
17.
17. But how many of them are available to do something?
7.
Just those 7. That's it. So what's the formula for table salt? Do we know that?
Delicious.
Its formula is delicious.
Yeah.
So I'm trying to get these things to get next to each other, but it won't move. There we go. Are you okay with me saying it's NaCl? Does this combination, does that make sense to you?
Yes.
The sodium has 1 electron to do something with, and the chlorine has 7 electrons to do something with. And what all the elements are trying to do is have no electrons around them to do anything, or have 8 electrons around them to do something. So why are these two guys happy they ran into each other?
Because there's 8 electrons.
This sodium is saying, hey, you want this electron, chlorine? And chlorine's got 1 missing hole right here. It needs to put 1 electron in that spot, and sodium is trying to give away 1 electron. So it does. And so this is why table salt is table salt, because they're both helping each other out. Whoa, that's huge. Let me bring that down some. So here's oxygen's Lewis structure. It's got those 6 electrons. And here's a hydrogen. Okay, so this oxygen wants to see 8 total electrons, but it's only got 6, and it's really reactive. And this hydrogen, it only has 1 electron, and I know that because it's in column number 1. And it doesn't want that electron. So what does this hydrogen do? Gives it to oxygen. And then what does this hydrogen do with its electron? Gives it to oxygen. So hydrogen doesn't have any of those electrons around it anymore, and that makes it happy. And now oxygen gets this electron and puts it right there, and that electron and puts it right there, and now now the oxygen is happy. So everybody's happy, and what molecule did we just make?
H2O, water.
We just made water, right? And
It's okay. So is 8 is that just like a magic number? Like they always want to have like 8?
yep, pretty much. Almost all of them are looking to have 8. We'll talk later about why the molecule itself is bent like that, but
but it is actually a bent structure. And that makes water super weird, which turns out to be really, really good for everybody living on Earth, that it's super weird. Okay. I think that's probably all I got for tonight.